Welcome back everybody to another video lecture from Ms. Simino. This is the third video in the equilibrium series. Today the main topic that we're going to talk about is calculating KSAP. We're also going to talk a little bit about the common ion effect. So here's our more formal objective for today. It says describe the relationship between the solubility product constant and the solubility of a compound. So we're going to be able to take our KSAP value and determine how soluble or how much of a substance will dissolve. We'll also be able to use those values to help us predict whether precipitation will occur when two salt solutions are mixed. So to start off with, our solubility product constant. Ionic compounds, also called salts, differ in their solubilities. We know this. We can put some things in water and some will dissolve, others are only going to dissolve slightly, or maybe it looks like they don't dissolve at all. If they look like they're not dissolving at all, we'll call them insoluble, but many of them actually dissolve to a very small extent. So sometimes you might hear the term that a salt is slightly soluble or sparingly soluble in water. So on this slide, we're learning to calculate the KSP value. You'll notice if you look at down here, you're like, okay, this looks just like the equilibrium expression that we were just writing in the previous lecture, and it is. So let's go ahead and see how we do this. So here's our equation. Here's silver chloride in equilibrium producing its ions. So if we were to write the equilibrium expression for it, it would look for something like this. But hopefully one of the things that you notice is our AgCl here. What's the physical state? It's a solid. Remember, we don't include those when we're doing our equilibrium expressions, and so now we won't be including them in our solubility product constants. And just as a quick reminder, remember we're putting our products, our concentration of our products over our concentration of our reactants. This slide is giving us a reason for why we're not including that silver chloride in our equilibrium, our KSP value. So let's go ahead and look at it. It says silver chloride existed as a solid material and is not in solution, so therefore it equals a constant concentration. The concentration of the silver chloride is constant as long as some undissolved solid is present. Same with any pure liquid. It does not change their concentrations. So by multiplying the two constants, a new constant can be developed, and this is called the solubility product constant. So if we look over here, this is really like what we're writing here. So remember just a second ago when we were writing our equilibrium expression, I said it was your products over your reactants. Well, since your reactant is going to equal 1 in that case, this is just what your expression is going to look like. So once you've determined the value of your solubility product constant, what does that value mean? Well, here we're talking that values of solubility product constants are given for some common slightly soluble salts in your book. No big deal. We said that our KSP value is this, and you can see if we have this numeric number here, do you guys see how this is a really small value? So it says the smaller the numeric value of your KSP, the lower the solubility of the compound. So hopefully you remember from when we were talking about Le Chatelier's principle and the K value. If your K value is bigger than 1, it was favoring the products. If your K value is smaller than 1, it was going to favor the reactants. Well, in this case, we have a very small value, so it's clearly smaller than 1. So it's going to favor the reactants. And this is making sense. So if we have low solubility, remember that your ions, it's going to only make a few ions, or it's only going to break apart slightly. So our solid here is breaking apart into its ions. So if we are favoring this, we are going to have very few ions in solution, meaning have a low solubility. And since this value is so low, we would generally say that silver chloride is insoluble. And if you guys remember back to some of our solubility rules we were doing earlier this year, silver chloride was one of those guys that was insoluble. Now we will be having some of these problems in class, but here are the steps for how to calculate the solubility product constant. First, you want to write the balanced equation which splits the chemical into its ions. Write the equilibrium expression and fill in the known values and calculate your answer. So it's pretty simple. Here are a few reminders for writing that solubility constant. Don't ever include pure liquids or solids. Remember, we just talked about that. That's because their concentrations are going to remain the same and the value for them would just be 1. Do not include any substance with an L after it. Sometimes you can see like these guys that have L. This one's actually really common. Or any substance which is a solid. So like we kind of said that. So here are some common ones that you might see. So make sure that you do not include them in your solubility product constant. So if you're not including those things that do not change, you may want to make sure that you always are including things that can change. And so the things that you're definitely including in that solubility product are gases and aqueous substances. So finally, I wanted to mention this common ion effect. This is something that can happen if it's a common ion, two substances are going to have the same ion in solution. And if you remember back to Le Chatelier's principle, the idea was that if you were adding more of a reactant, it was going to shift your reaction towards the products, or if you added more of the product, it was going to shift it towards the reactants. So here's an example of what can happen. It says here that a common ion is an ion that is found in both salts in the solution. So if you have a solution of lead chromate and you add some lead nitrate, lead is going to be your common ion. This causes a shift in the equilibrium due to the Le Chatelier principle regarding concentration, and it's called the common ion effect. So along with this common ion effect, we can talk about whether a precipitate will form. So if we have a calculated ion product concentration and it's greater than the accepted value for your KSAP, then a precipitate will form. So as always, you guys, I hope this video was helpful. Remember to write down any questions that you have, and we'll be looking back at these notes when we're calculating our problems in class. Good night.